All right, let's get started. Welcome, Lucia. Today we're gonna be solving a daily from a couple of days back. I share the link, it's pinned, and it's called Count Vowels Permutation. It's a hard one, so bear with me. So given an integer n, your task is to count how many strings of length n can be formed under the following rules. And each character is a lowercase vowel, so A, E, I, O, and U. There are 5 vowels, and you have like 5 other rules. So A may only be followed by an E, E may only be followed by an A or an I may not be followed by another I, O may only be followed by I or a U, and so on. And since the answer may be too large, return it mod 10 to the 9 plus 7, which is the usual modulo. And n can be up to 20,000. So that's good. We get 3 examples for very small n, 1, 2, and 5. So of course, when n is 1, you can only have 1 letter, and there are 5 of them. There are no restrictions other than that, so the answer is 5. And if you have 2, then the answer is 10. So let's try to first to translate these rules. Maybe we can write them down in a more... So this is not working as expected. Let's see. Well, anyways, so we can write this down as a graph where each letter is whoa. Where each letter, so we have a node for A. This is a little, so it's 300. Okay. Maybe I zoomed it accidentally. Let me move this here. Okay, so we have A and B, no, not B, E, O, and I, and U. Doesn't matter what order we do. So what are the rules? The rules are that A may only be followed by an E. So that means that from A we have an edge that goes to E only. It's a directed edge. Then E goes to A or I. So here we can go back, or we can go to I. Then I may not be followed by another I, so that means that it can go to every other letter, but not to itself. So we can make this a bidirectional edge, and it can go to U, and it can go to O. And O may only be followed by I and U, Okay, so this is again bidirectional, and O can go to U. And finally, U can only go to A. So let's do one outside. Okay, so this is the translation of the rules in terms of graph theory, in terms of a directed graph with 5 nodes. So we can represent this in a different way as a, well, one of the ways to represent graphs is in terms of an adjacency matrix. Okay, so we're gonna have this matrix where A, E, I, O, and U, and again E, I, O, and U. And so, well, there's no loop, no edge that goes from one node to itself, so the diagonal is not going to have any edge. So A can only go to E. So this is the edge that corresponds to A, from A, that goes from A to E, and there's no other. Then E can go to A or I. So this is the corresponding row. I can go to A. Well, it can go to anyone. All right. So and O. So I'm doing this again just to make sure that we are understanding the problem. So E goes to O goes to I or U, and U only goes to A. So this is the corresponding. So notice that now a path, for example, here we have all the paths of length 2, so it's A and E. So yeah, notice that the strings that are being generated are correspond to paths on our graph. So A, E is going from here to here, and so on. So essentially, we want to count how many paths are there of length n, of some length, but notice that there's a detail which, for example, this string has n is 2 here, but the length of the path is only 1, because the path length is counted as one edge. So we want to count, so how many paths of length n minus 1. So this is what we want to find, and this is a very well-known problem. So this is where I when I go back to some theory that it's useful to know, but I'm going to explain why. So it turns out my claim is that so if we call this matrix A, so it turns out that A to the n minus 1 has all the paths. So if you consider the element I so on row I and column J is the number of paths from I to J of length. So I'm not okay. So of length n minus 1. So well, why is the case? So it's important to understand so that if you don't remember it exactly, you have an intuition, but then you can, if you remember why it was true, then you can reconstruct it. So here again, you can prove this by induction. So in the case of A to the 1, it is obviously true because the edges, we have a 1 when there is an edge from a node to another, and that's how many paths there are. So from A to A, there is no path of length 1, but from A to E, there is 1, and so on. So the case of A to the 1, it's trivial. Even the case of A to the 0, which if you remember from linear algebra, it's going to be the identity matrix, which is all ones in the diagonal. And it makes sense here because if you have zero edges, there's only one path from A to A, and there's no path from A to any other node, and the same goes for E and for every other node. So in the case of A to the 0, it's also true. So now what happens in the case of A to the n? So we can write A to the n as A to the n minus 1 times A. And if we assume that the property holds for A to the n minus 1, which means that, well, this counts the number of paths from I to J and so on, then we can, if you remember how matrices are multiplied, this is the way. So the element I, row I and column J of A to the n is going to be the sum for all the possible k's of A to the n minus 1 of from I to this middle node K times A from K to J. Okay, so well, think about this. So here, this, like we established, this is counting the number of paths from I to K for every K, of length n minus 1. And then this is counting all the paths of length 1 from k to j. So for every path that goes from I to k, you can combine it with every path that goes from k to j. That's why we multiply. And when we multiply, we get the paths from I to j of length n. Okay, so that's why this is true here, this, and that's how we are going to solve this. So that means that our problem boils down to computing this. And this is going to give us all the combinations. So how do we compute this fast? Because n, well, I mean, n is not that big in this case, but as you may know, there is a fast way, fast exponentiation, which is you can do it in order logarithmic of n, log of n, and well, I'll explain a little bit how it works before diving into the code. But notice that this doesn't have to do with matrices of graph. This is just an algorithm for fast exponentiation. So the idea is that if you have a to the n, you can write it down. So n, you can decompose it as 2 to the q plus r, with r being the remainder when divided by 2, which has to be either 0 or 1. And so you can replace n by this expression, and by the rules of the exponents, this is equivalent to a squared to the q times a to the r. And the algorithm is based on this because at each step, if the exponent is it's odd, that means that r is going to be 1, so you multiply by a, and then you compute the square of a, and you have a new exponent, which is n divided by 2. And you iterate. And since you are dividing by 2 on each iteration, the order of complexity is logarithmic. Okay, so well, now after all of that, let's try to code it. So how do we do this? So let's first write the matrix. So this is just copying what we wrote in the board. So a was, so I'm going to do this for the third time, but sorry about that, but so that we can understand what we're doing. So a goes to e, then e goes to a or I, then I goes to everything except itself, O goes to I or U, and U goes to A only. Alright, so this is our matrix. So notice that the size of all the matrices here are going to be squares. square matrices and size 5. So let's have a convenient constant for that. Also, we're gonna do the operations modulo 10 to the 9 plus 7. So those are our constants. And now we are going to assume that we have a power function that works with matrices. Let's not do, well, yeah, let's not do capital. Let's reserve that for constants. So anyways, let's imagine that we have that already. And so what we said is that the answer is going to be this, right? Well, not exactly the answer, but that's going to be the matrix. And then since we are not, we can start from any node and end on any node, then we essentially have to add up the matrix, the resulting matrix, to get the result. So here we're gonna have all the paths from R to C, and we have to make sure that we mod it. So that is essentially the code there. So now we need to, so this power function, it's based on the formula that I explained here. But you can have this in your library of code. I mean, why do I have to? So in Python, you already have power functions, but the difference is that I want to apply it to matrices here. So that's why I need to write my own. So usually, so the code for this, for numbers, it's going to look like this. So if n is odd, hey, Sij, thanks for the follow. So here in this case we want to multiply by, so res by a, and a we wanted to square it, and we want to divide n by 2. So this would be with numbers, okay? But we haven't overloaded the multiplication operators. So we need to change, for example, 1, instead of a 1, we want the identity matrix, which is going to be, like I said, I think I need to, yeah. So for the rows and for the columns, and if they are the same, I want a 1, and otherwise I want a 0. So this is the identity, and here I want to have a multiplication matrix multiplication function that I'm gonna need. So that's it. And now we need our mul function, which is going to be what we establish here, this formula, the summation. Maybe in Python we can write it. Yeah, let's see. So those are the rows, then these are the columns, and for every position in the matrix we want to sum. Well, I guess we use I and j before, and k was the intermediate node, which also has n possibilities, and here we want a of I and b kj. Yeah, the only thing is that we need to do mod again here, and I think that's it. And here, no, I think if we do that there, we are covered in terms of mod. So let's see if this works. Passes the examples, and it passes. Cool, and it's almost 99%. That's cool. I wouldn't expect that to be faster than most of the Python. Nice, damn. Thank you guys. Yeah, I think the code is pretty clean. You have to be careful when you create this matrix. Make sure that you are translating the bullets, the rules correctly. But yeah, I think this is a cool problem because this is a very general technique. So this works for counting paths of a specific length on a graph, on any graph. So that's a tool that you can incorporate to your toolkit. Anytime you want to count paths on a graph, remember this. TTP, and it's slower. All right. Yeah, that's interesting. I'm not sure. Well, I guess that since we are doing the logarithmic, so yes, I guess that's why this is faster, because I could have done the multiplication linearly. Probably that would work. Yeah, that should definitely work. But I guess that by doing this makes it doing this by dividing by 2 every time and doing it logarithmically. I think that's what makes it fast. So yeah. So yeah, this was my first approach because I'm familiar with this method. But of course, if you can do it with the P, that's good too. Whatever gets accepted, but it's always good to learn other ways, to learn also this technique, even if you solve it in a different way. So yeah, so this is very general. That was my point. This is very general, so make sure that you know this. So it comes up in problems, in LeetCode problems. And also this one, the fast exponentiation it's called by squaring because of what we did here. We're squaring the base number. So this is a very, very important algorithm to know, and very simple. Once you know this explanation, it's very easy to implement. So yes, that's all I have. Thank you, Lucia. So see you in the next one. Bye bye.